So my project is on the logistic equation and how it can measure population growth in the United States. The logistic growth model was first discovered in 1920 and then rediscovered by American population ecologists Raymond Pearl and Lowell Reed. They compared population data of the United States between 1790 and 1920 using the logistic growth equation, finding that the numbers produced by the equation and the real data matched quite well. One man who had great influence in the logistic growth model field is Sir Robert May. Robert May was born in Sydney, Australia in 1936. He is an extremely versatile and experienced scientist. He started his science career in an undergrad for chemical engineering. May then switched to physics for his doctoral work. He received his PhD for theoretical physics in 1959 and soon after became a professor. He then switched again from physics research to population ecology. May became the world's foremost authority in mathematical ecology and was appointed professor of biology at Princeton. While working at Princeton, May produced his pioneering work in mathematical models of population growth. The conventional wisdom at the time was that to model a complex ecosystem, one needs a complicated mathematical model, and the more complexity shown in the system, the more sophisticated the question and variables of the model need to be. It was believed that a simple mathematical model could not possibly reproduce complicated patterns of behavior. The logistics growth model is essentially very simple, but is able to measure complexity within our population and its growth. May wrote a revolutionary paper called Simple Mathematical Models with Complicated Dynamics. May showed that the extremely simple logistic growth model could exhibit surprisingly exotic patterns, such as periodicity, bifurcation, and seemingly random fluctuation. May paved the way for a new and revolutionary branch of mathematics called chaos theory. May went on to work at Cambridge, being knighted and receiving many prestigious awards. For measuring populations, exponential and linear models are inadequate. Linear growth models are only okay for situations where the amount of growth is constant. For example, inanimate objects, garbage, toys produced, or sales figures. The linear model cannot account for breeding and the patterns associated with breeding. Exponential growth represents a case in which there is unrestrained breeding, compounding money, or early stages of actual animal population. However, animal populations have to level off as capacity is reached. In population biology, it is not generally the case that population growth is constant and does not depend on density of population in its environment. As population density increases, there is less room to grow, and there is more competition for resources. The growth rate will tend to taper off. Sometimes the population density is high, so that resources are scarce or have depleted, leading to population decay or, in the extreme, extinction. Biologists use the term carrying capacity to describe the total saturation point of a habitat. The carrying capacity is denoted as capital C. It is a ceiling or a population living in a given habitat. By definition, the population will never exceed C. Population is denoted as capital P sub n. C minus P sub n is the absolute amount of elbow room remaining for a population or its availability to continue to grow before carrying capacity is reached. It can also be represented as a percentage of the carrying capacity by dividing by C. When the elbow room is very high, close to 100%, the population can breed without restraints. The exponential growth equation P sub n plus 1 equals R times P sub n is a good measure of growth. R is a growth rate or a constant growth parameter. The key idea to the logistic equation growth model is that this growth rate decreases in direct proportion to the amount of elbow room. The p-values are the fractions of the carrying capacity taken up by the population. Here is the logistic growth equation. P sub n plus 1 is the population after a generation, equals R, the growth parameter, times 1 minus P sub n times P sub n. Here is also a graph of an example of logistic growth in the United States for AIDS. In 1950, behavioral psychologist John B. Calhoun studied the effects of population density on growth rates. He showed that when rats were placed in a closed environment, their behavior and growth rates were normal as long as the rats were not too crowded. When the environment became too crowded, the rats exhibited abnormal behavior, such as infertility and cannibalism. This behavior put a brake on growth. Example 1. Fish farming is a big business these days, so you decide to give it a try. You have access to a large natural pond in which you plan to set up a rainbow trout hatchery. The carrying capacity of the pond is 10,000 fish, and the growth parameter of this type of rainbow trout is 2.5. We will use a logistic equation to model the growth of the fish population in your pond. Start by seeding the pond with an initial population of 2,000 trout. That is 20% of the pond's carrying capacity. P1 equals 2.5, the growth parameter, times 1 minus P2, the initial population, times P2, the initial population, equals 0.4. The population of the pond has doubled in 1 year. The trout population is 4,000. Comparing this to the model, you can see the rapid increase shown in the beginning stages. P2 equals 2.5 times 1 minus P4, the population from P1, times 0.4 equals 0.6. The population is now at 60% capacity after the second year. P3 equals 2.5 times 1 minus 0.6, the population from P2, times 0.6, which equals 0.6. P4 equals 2.5 times 1 minus 0.6 times 0.6, which equals 0.6. The hatchery is stuck at 60%. This is not going to change unless external forces come into play. This is described as stable equilibrium. Example 2. The p-values will actually change if there is a different initial population. Consider the same setting as the previous slide with the same r value, but the initial population is increased to 3,000, 30% of the carrying capacity. Now how will the population grow? Notice the differences between P2 and P3 and how it decreases to P3. Why are there these differences? Why is it increasing and decreasing? Something is different here with the trout population. It appears to be fluctuating, but always floating around 0.6. The value 0.6 is an attracting point of the population sequence. If we started with 70% capacity, complementary to 30%, we would end up with the same population values. You get bored of trout. Goldfish are easier to breed, so you use a growth parameter of 3.1 and start by seeding the tank with 20% capacity. Look what happens with 16 p-values. What is graphed appears to be unexpected, an interesting pattern. After a few breeding seasons, the population settles into a two-cycle alternating between a high population period at 0.765 and a low population at 0.557. This shows the oscillating nature of the population sequence. Even more complex cyclical patterns are possible when we increase the growth parameter a little bit. Say goodbye to fish farming. Now we are interested in entomology, the study of insects. The population growth parameter of beetles is 3.5. The seed will be a PO value of 0.44. The seed value doesn't really matter though. Look at these P values, the first 25. This data shows a pattern. The population will repeat itself in a 4-period cycle. The cyclical behavior exhibited is not unusual, and many insect populations follow cyclical patterns of various lengths. 7 years for locusts, 17 years for cicadas, etc. In the logistic growth model, the highest allowed value of the growth parameter is r equals 4. The chaos theory exhibits this, which will be explained later. Here is a real-world example. This data comes from Duke University. The first graph shows blue points that are the data collected, and then the red line is the predicted growth using the logistic growth equation. The second graph is the rest of the data plotted through 1940. It matches accurately to the prediction, showing that the logistic equation is a good representation of growth. Here is chaos theory. These are a few pictures that illustrate some of the types of chaos that can occur. Chaos theory. The branch of mathematics that deals with complex systems whose behavior is highly sensitive to slight changes in conditions, so that small alterations can give rise to strikingly great consequences. Here is an example of chaos. Start with a PO value of 0.2 and look at the p-values generated by the logistic equation when r equals 4. Here are the first 20. The surprise here is the absence of any apparent pattern. No matter how much further we continue computing the p-values, we will find no predictable pattern. The p-values look random, but they are actually coming from the simple logistic equation. Notice the jaggedness in the beginning, but how it suddenly drops down around 13, 14, 15, 16 minutes, and then jumps back up at 20.